Dr. Ghosh, he has completed his PhD from the Jadavpur University, Kolkata, West Bengal. Afterwards, he moved to USA for his first postdoctoral research in the UPRH USA, PR USA. Followed by he was in Bowling Green University, Ohio State, USA for his second postdoctoral research. After returning back from USA, he joined as a visiting fellow at TIFR Mumbai, followed by assistant professor in BITS Pilani, Goa, and then he moved to VNIT Nagpur, and presently he is the professor and head of the Department of Chemistry, VNIT Nagpur. So his research interest mostly involved in the physical and synthetic chemistry for the steady state and time resolved fluorescence spectroscopy, single molecule spectroscopy, confocal imaging, and fiber microscopy. As you can see, its title of today's talk is Theragnostic Approach in Medicinal Chemistry. So with that, I welcome Dr. Ghosh for the presentations. Now it's all yours.
Yeah, thank you, Sandipan, coordinator, and I think you can you see some resemblance with the stand up, please? Resemblance with me, and it's so much that people cannot distinguish between Sandipan and me, and somewhere in some international conference they put his name and my picture. And even here, some people came to me, something like that. Okay, so he's my younger brother only. So anyway, so today's talk is Theragnostic Approaches in Medicinal Chemistry. Okay, so this is, I think, last 4 days you have you know all about this. There is a long route of drug discovery and development. This is the conventional drug discovery things, which actually takes up to, if you add these 2 to 5 all these years, so then ultimately you will get it almost 20 years. It takes 18 to 20 years. This was earlier. So now everything is moved into its rational drug designing. Okay, so rational drug designing because of time, and on the blessing of rational drug design only. I think this must be switched off or something. Can I switch it off? Switched off. Okay. So by the blessings of rational drug designing or computer-aided drug designing, we are able to get our COVID vaccine within 1.5 years or so. So this is a small route, but I think enough it is discussed for that. But I'll tell you something now, another approach which is called Theragnostic approach. So the name itself says everything for everybody. Suppose I think I tell my students, what is your name? And anything you see, the name itself describes the thing. Okay, so the theragnostics it has 2 parts actually. It's a therapy. This is theragnostic. So it's a therapeutic as well as diagnostic things. So the one part of the molecule will act as a therapeutic activity. It will show its therapeutic activity, and another part of the molecules will help us to diagnose the thing. Okay, so this total approach is a theragnostic approach. So there are like here, this is a chemotherapeutic drug, and then proteins. You can take anything about the therapeutic things, and fluorescence probe, quantum dots, gold nanoparticles, they are used for the diagnostics purpose. So the overall therapeutic and diagnosis give you a so here we will talk about not only anti-cancer, mostly anti-cancer, because within 1 hour or 1.5 hours I cannot tell you the whole thing. So we'll talk about this, how this theragnostic approach working, and some case studies. Of course, our own lab we do that. So here usually what it is a fluorescent probe or cancer targeting ligands. Is both are added together. I'll take 1 minute. I think 1 tab will be laser.
Yes.
And 2 tab is highlighter.
Yes.
So can you do that?
What do you want?
Yeah, I want the laser pointer.
They're not changing anymore.
Yeah. Anyway, it's fine.
But you have to take this spotlight.
Yeah, a spotlight as well as it also works as a laser, but you have to do it from there. Thank you so much. No, same things. You have to change it from there. So now it will, this laser will work. Oh no, it's fine. This also works like two ways.
Yes, in fact it works 3 ways, but it,
Absolutely.
but had to properly install
Couple it.
things like that.
Thank you so much. Yeah. So the usually the cancer this fluorophores and cancer targeting ligands is used together, is coupled together for anti-cancer theragnostics. Means here the therapeutic activity is the anti-cancer activity, and the diagnostics activity is all like the diagnostics purpose we use. Suppose the real-time monitoring of the cell and all. So usually the usual design is suppose this targeting ligand, and then there is a spacer unit, and then we add a fluorophore, then cleavable linker and therapeutic overhead. This is the overall conventional things what people are doing. I'll tell you something else apart from this. So here 2 molecules are attached by something. So by a cleavable, by a spacer, as well as some cleavable linker and therapeutic overhead that is usually used for the delivery of the molecule to the cell. And so the design strategy and drug release mechanism also is taken care of by these therapeutic things, by using some specific markers and receptor mediated endocytosis and all. And then, so development of theragnostic on the basis of cleavable mode of linkers are, the linker can be a thiol mediated linker, H2OD2 to mediated release, enzyme activated release, pH triggered theragnostics, light activated theragnostics, NIR dye based theragnostics, aptamer based theragnostics also. This is all linkers. What you have seen here, so the spacer and the cleavable linker, so this part people use those bonds because of in the overexpression of suppose enzyme activated release. The overexpression of some enzyme in a particular tumor will help this linker to cut that. So basically it's the whole thing will go, and then somebody will cut from the somewhere else where the other part will go up, and this part will show its therapeutic activity, the other part will show the imaging activity. So you do no need to use the co-staining. But here is to some extent co-staining is there. So the thiol mediated linkers, there are so many examples and so many plus minuses of it, pros and cons. I'll not go in details of that. You can Google it, you will get it. And then therapeutic with disulfide bond targeting ligands also. There are lots of molecules are available like this molecule. So the prodrug and fluorophore, they are attached with the linkage of disulfide bonds, and it will cut there, and then it will show the activity, therapeutic activity as well as diagnostic purpose. So another one is therapeutic ligands without targeting ligands. This is H2 mediated release. That's also, and this is enzyme activated release, as I told you just few minutes back. Actually, we are working on it also from some of our molecule. And then pH triggered theragnostics are also available. So this is exactly work in exactly the same fashion. In certain pH this fellow will work. Okay, so once this pH, normally the tumor pH is lower pH. It's pH 5.5 and so all. So light activated theragnostics is also used, some photosensitizer attached with this particular thing, and then it is activated. It means this photosensitizer triplet state. Actually, photosensitizer usually use porphyrin, means the phthalocyanins, chlorines, where triplet energy is exactly similar to the energy of the oxygen, triplet energy of the oxygen. So oxygen takes the triplet energy and get it converted into the singlet oxygen, and singlet oxygen does the rest of the things. So usually this kind of things used in the PDT, means photodynamic therapy. Now people are clubbing with this photosensitizer with quinones, or the part of some part of the chemotherapeutic drug cuts into it, attached to the photosensitizer, or do not attach. Sometimes they push together, and this is photosensitized. The molecule is photosensitized and it kills the cell. So, and the fluorophores are used normally the rhodamine, coumarin base, fluorescein base, naphthalimide base and all. So, these are the some scaffolds. So, the key points for this theragnostics are the tumor specific receptor. Don't worry, I am going little bit fast because we have many things to tell you. But if you have any question, you can stop me anytime. Because ultimately I am a teacher, we are doing this from day and night through means 365 days almost. So, no problem at all. And so, the tumor key points are tumor specific receptor, receptor overacts in the cancer. These are the points you have to take care when you are designing a theragnostic molecules. And what will be the mediator means the thiol mediated, enzyme mediated or whatever. So, now what I am going to tell you, we went one step ahead. Okay, so we want some molecule. So far, whatever we have told, there is a therapeutic part and there is an probing part. So these two are attached with each other by a cleavable bond, and we do cleavage, we do cut it as per the medium it is. Okay, so but here we want to develop some molecules, or we have developed some molecule which is a small molecule. It's a therapeutic drug, as well as by its own fluorescence, own luminescence, we can image it, so that we can avoid the co-staining. We don't need any other fluorophore to attach with it and cut with that. Okay, so here and that is not only that. Only the fluorescence imaging, we have used, I use the term small molecule based therapeutic biluminophore. Usually first thing we started with the luminophore, to be very honest, the only fluorescence imaging capability which molecule have, but gradually we have developed some biluminophore compound also. So I will tell you what is biluminophore in the next slides probably. So here we can means the therapeutic activity also is taken care of, and diagnostics also properties also taken care of by virtue of its own fluorescence as well as phosphorescence too. So that's why we say it's a biluminophore. It has two ways. So somehow I'll show the mechanism. So we control the molecule such a way that sometimes it will show the fluorescence, sometimes it will show the phosphorescence. So wherever it is needed. So and we use it for all these things, and for the Alzheimer's disease, for the previous one was, sorry. Yeah, so it's a DNA interactions and some other cancer cell line detection as well as killing and imaging too. So the simple comprehensive approach towards the drug discovery of the theragnostication, this is the approach we follow in our lab. So we essentially first thing what we do is we select the potential bioactive skeleton. So we select the skeleton, and then we go for CADD. Okay, so before the synthetic skeleton, we of course we do some virtual screening, and we take care almost 50 or even more than that molecules, and ultimately we design some molecules. We do dock the molecules with the target receptor. We go for the simulation studies also, and then if there is a chance, means from there if we can sense that this molecule may work, there are many molecules may work, but it may not work also. There is a possibility it will not work, but somehow you have to go for the positive side only. So we go for the docking and simulation studies, and then we select some molecule and go for the synthesis. Synthesis also we take care, not necessarily that the molecule you design and you have very good result in silico studies, you will be able to synthesize that. Sometimes, many times we failed. We have taken help of some specific group who are in the industry, even they also failed. So that also happened, but the failure percentage is 20%, success percent is 80%, even more. So we always have to go for the positive thing only. So then we go for the okay, after the synthesis, two things we go parallelly. One thing is to see this is the effect, therapeutic activity. So if suppose I am targeting that I'm thinking it's an anti-cancer agent. So then we of course we study it in the cell viability assay, cell and all those things, therapeutic to monitor the therapeutic activity, and same time, since it is a theragnostics, we are designing the theragnostic molecules, and by virtue of its own fluorescence, so the photophysics of that molecule is extremely necessary, because we will see the therapeutic activity of that molecule, and by the emission characteristics of that molecule itself. So we are not going to include any other molecule with this, only one molecule, which is a small molecule, without use of any co-staining. So its photophysics is very much necessary. Not only that, its photophysics, solvation and solvation dynamics. You know what, in this journey what we have seen, some molecules after means it's some structure in some media, once you put into water or somewhere else, its structure changes. So how do you know that this structure will work or not? Okay, so and which fashion? So if we start and then we go, I'll come to there, and then we go for the interaction with the target receptor, in vitro interaction. So this is by optical spectroscopy and molecular docking and M2 simulation, that actually we do before, then extensively we do after this synthesis, and then antiproliferative activity with the cancer cell lines or whatever we are looking for, and then imaging, inspection of its imaging capabilities. Then we come back to the design again, if there is anything to be changed, and it always needs some improvement. Okay, so this is the overall journey, and then these approaches we do by UV visual absorption, steady state fluorescence, anisotropy, fluorescence anisotropy, time dissolved fluorescence, confocal microscopy, FTIR, gel electrophoresis, and many other methods. All biochemical approaches are also we do along with the synthesis and its characterization auto high. So that is already there. Until and unless you do it, you cannot go do these things. Okay. So this is one case. Here the strategic design of a bichromophoric naphthalimide. So we have taken two part. One is the naphthalimide molecule, which is a classical intercalator, and another is a benzothiazole group. So this idea came in my mind actually 5F403. There is a molecule. It's the 4 stages of clinical trial when I started this particular project. So then we add this. Okay, and we got this particular therapeutic luminophore, which has a highly fluorescence. So this particular molecule, so we got this therapeutic luminophore, which does not have only the high fluorescence, as well as it has a synthetic feasibility, very easy to synthesize, and quantumly is not that high, but we can optimize the process to get it. That is a particular medicinal chemistry person job to how to get, or industry person job how to get the more quantum yield. But here as a model we establish that this is possible, and it's a quantum yield is okay, means it's not very less. So then we went for this. So to get this compound, we as I told you, we have designed many compounds, and we went for docking. We taken care of the docking score, we taken care of its synthetic feasibility, and we went for synthesis of this particular compound. So this compound ultimately we have synthesized and went for this. So by this method, okay, this is a one-spot condensation reaction. And it's the compounds are also means reactants are also not costly. Is that so? Then we went for all this in vitro studies, means the photophysics to explore the possibility of the imaging, as well as any structural change if it does occurs in any solvent. So we explored, we study this molecule from hexane to water. Almost 12 to 15 solvents we put this molecule, and we study its photophysics. And if you see here, so I have given some representative solvents. If you see here, from I believe this is dioxane, and from here to methanol, the emission intensity is increasing with a red shift. And if you see in water, this is compared to the methanol, it's almost 5 times 2500, this is 500. So in water, it's a highly fluorescence. Okay, so although it's a non-polar media, it's less fluorescence. That also considerable fluorescence, but here it is used. Then definitely we went for what is the reason for this. So then we did some quantum chemical calculation. This is a quantum chemical calculation on the basis of this DFT and TDDFT based and several basis sets we used to optimize the molecules. And then we have seen that this molecule actually in the ground state, these two parts are perpendicular to each other. When it got excited, this is the HOMO-LUMO diagram of this particular molecule. You see the charges, what was over here, it is getting transferred to here in the excited state. And the molecules, this particular molecules becomes almost coplanar, not 180 degree, I think 178 degree or something. And not only that, same time the charge from the benzothiazole ring is going to this naphthalimoid moiety. And as so later on we have established and this is a potential energy curve of that particular molecule with the changing the dihedral angle. Okay, so here if you see 90 degree in the ground state, the molecule is stable at 90 degree. This curve itself says the minima is here for ground state, and for the excited state minima is here. So from here, as I was telling you, this angle you can see. This angle is almost 178 degree. So what is happening if we later on, means I don't know whether I have added it or no. To make it short, I did not add all slides. So in brief, I am telling you. So this kind of enhancement in water we have explained in this way. So that in suppose once this charge is coming out from this one and going to the naphthalimoid moiety, and you see there are two oxygens there. So once you put in water, these oxygens form the hydrogen bond with the solvent molecule itself. And once this is from the hydrogen bond with the solvent molecule, these two oxygen, then this moiety becomes electron deficient. So it drags these electron clouds through this nitrogen molecule. And this nitrogen molecule, that time it got rehybridized from sp3 to sp2. So we say it's a rehybridized intramolecular charge transfer in the molecules, which actually helping the molecule to come in a coplanar mode and show this emission intensity with huge redshift. So this will help us for the to diagnostics purpose of the molecule. Okay, so the overall story is, to make cut short, the story is if we in the ground state the molecule is something like this, means it's a perpendicular to each other, two moieties, and it undergoes a conformational change, or I'll say rehybridized intermolecular charge transfer in the excited state, and then it emits from the RICT state to the ground state. So overall, that was the story. It's a donor acceptor system, and we can see it's a molecular rotor. This kind of molecular rotor, I have some other molecules also, which can be used for the viscosities, micro viscosity measurement of the cell. And not only that, once you put into the cell, it's some medium, it acts differently, as well as the polarity of with the polarity of the molecule, this molecule shows the sensitivity. So you know, for any disease, specifically cancer, when it is forming, a tumor is forming, in the early detection, forget it. Before the detection also, if some viscosity of that particular region changes, polarity of that particular environment changes, so all those things changes. Okay, so even after the tumor is formed, you can find out the polarity or viscosity of that particular environment by this kind of molecules. So this is not only an imaging characteristics, it will give us the viscosity sensor, polarity sensor measurements kind of things. So then as I told you, it's an bioluminescence characteristics of this molecule. We went further to see that this molecules is giving a high phosphorescence in nonpolar solvents. I showed you that it is a highly fluorescence in water-like environment, and low emission is in nonpolar environment. so we went for this, what is the reason? What is the reason of the, for this particular thing? So we went there, and then we saw that this is because of the intramolecular halogen bonding interactions. This molecule, it will come automatically, or just, it's okay, so I can have some water in between. So you might have a question that that what is the need of this to see all these detailed photophysics, right? Because mostly the audience from the biology side, if I see, or even not, so if it is therapeutic active, then it's fine. The straightforward answer is that to see the therapeutic, the mechanism of the interaction. I'll show you. We have studied that. So the mechanism of interaction of this particular molecule is we have monitored by its emission characteristics. Okay, so that's why the emission characteristics we have established first. So the synthesis, so we do synthesis of any molecule with purpose till the mechanism we go. So then yeah, so then we went for the all details of this possible mechanism of this particular thing. Why does it show the phosphorescence and all? So all those things we have considered, the ring expansion, oxidant formation, we put it even the polymer film also, but we identified that this is an intramolecular halogen bonding interactions are the responsible thing to show the phosphorescence in a rigid medium. So the bottom line is, so if you, this one, so it's there is at room temperature solvent, there is a fighting between the fluorescence and the phosphorescence. If you rigidify the molecule in a non-planar state, it molecules becomes in a non-planar state and it gives phosphorescence. If you allow you to conformationally relax, so if you do not allow the if you put this conformational restriction or do not allow this molecule to conformationally relax to come this planar state, it gives the fluorescence. And if you do not, so conformational restriction, it will give you phosphorescence. This is a fluorescence, phosphorescence on off. So the details are in this particular paper. So if you want, I can give you this reference also. And then we went for this therapeutic activity. Okay, we put these molecules in several cancer cell lines, and we got the maximum. It's a good result in this A459 cells, and we have seen this, and this kind of decrement in your cell numbers. But here, when I saw the thing is that when I got this data as well as this data, so what I didn't look, okay, I was happy with this curve. So this means there is a IC50 value is okay, considerable, but what was strike me is the morphological change in the cell of the cancer cells. If you see nicely, the cells are shrinking up. The cell, the shape has been changed. Is a rounded up. So and it's like it brusted or something. So that hits us. So what is this? If this is so then definitely there is a cytokeratin disturbances, because if not, then cell will not be this way. It will, the number reduction will be means it will be there. And then we went for the once we got this sensation, then we went for, okay, so let's take the cytokeratin protein, which is tubulin, and so the morphological changes suggest that the cell death and cytokeratin disturbances, as I told you, which is tubulin and actin. So we take the tubulin protein, so as well as actin, and then we perform the detailed study with the interaction of this particular molecule with the tubulins, with the preformed microtubules, as well as the tubulin also. So whether it's we want to see whether it's inhibiting the formation of the tubulin polymerization, or it is disrupting the preformed microtubules. Okay, so this is the antimitotics. So we thought that it may work as antimitotic drugs also. So you know already how this antimitotic drug works. So these are cell cycles is a G1, G2, ACE and M phase. So in their prophase, metaphase, anaphase and telophase. So the spindle formation is there, and then there is a cell division is there. So the molecule which act somewhere in here and changes this, stop this thing, are usually antimitotic drugs. Okay, those are using now. So same way we went for. So this is the mechanism, how does it work. This is alpha beta, means the tubulin has a heterodimer, alpha beta heterodimer. Okay, so then we went for, okay, so this is the perturbation of cellular. To see that, to go further, we study this confocal images of, these are the confocal images of the A459 cell with my molecules. And if you see, this is the control, this is the, with the dose dependent manner we put, and now we did the control studies. So this is with tubulin only, and then DNA, this is the DNA, we merge this is control one. And if you see with our compound, this molecule, this particular bipolar nature is finished, and here is a complete formation of another thing, which means it's destroyed this tubulin structure. It attacks the previous slides whatever I have shown, the cell cycle, and means this particular part, and my molecules may act as an antimitotic agent. So then so dose dependent manner, so then we went for the further studies, in vitro studies, that whether it binds with tubulin, first thing we have to see. So then we saw that it is not only binding with tubulin. Okay, so this is the, what is this? This is the polymerization of tubulin assembly. So the black one, so this is for the students, since everyone is not very expertise in this field. So here, if you put this tubulin protein in a particular buffer, and now sometimes it forms microtubule. And once it forms the microtubule, its absorbance increases. So as the case for this black one here, this is without the molecule. And then we started adding our molecule in different concentration and see whether its microtubule formation is going on or not. And we see this microtubule formation is inhibiting, means the time it takes for this microtubule formation for this without the drug, without this molecule, and with this molecule is different. So my molecule is inhibiting the formation of a microtubule, a tubulin polymerization, not microtubule. Okay, so that means inhibition of tubulin into microtubules, the CBIQD, my molecule works. We did the reverse thing also. So we put this preformed microtubules. We allow the tubulin to form the microtubules, and then in the microtubule itself, we put our compound. So then we see, and then we monitor it with the emissions spectra. That's what here we use the DAPI emission actually, because that is the standard use for the microtubule depolymerization, we say. So this is, means the thing is that if it's a binding, it binds with something, the fluorophore DAPI, and my molecule can break this structure, the DAPI fluorescence goes down. So that's the thing happens here, this figure. So from here, both the slides we can say this molecules acts as a means tubulin polymerization inhibitor, as well as a depolymerization of the preformed microtubules also. Then we went further. So if it does so does it interact with tubulin? Does it bind with tubulin? If it is, then how it is? What is the strength? How strong it is? And where does it bind? That's also very, very important. And so then we went for this all spectroscopic studies of that particular molecule, and we found out the binding constant, which is reasonably good, not too high, not too less. And we found that this is the decrement of this fluorescence. We saw this molecule is binding with this particular tubulin protein. So then we went for the if it is binds, where does it bind? We take this the standard drug colchicine, vein blasting, because tubulin binds in some, there is this protein has some sites, right? Not everywhere it binds with the drug molecules or the any ligand. So it has sites, the colchicine binding sites, vein blasting binding sites. We did in vitro experiment with that. In the tubulin, we put colchicine and allow it to bind it to that once, and that also we monitored, it is binding, and after that we add our compound and the reverse as well. So whether there is any change in the fluorescence spectra, here with colchicine we have seen a lot of changes, whereas the vein blasting it does not. So that means the molecule here does not compete with the vein blasting, rather it does compete with the colchicine. So that means this is going to the colchicine binding sites, or this may go. Okay, so then we went for the further things. If it does bind, so we have established the binding, we have seen its therapeutic activity. Now actually we are looking at the mechanism, which mechanism this particular molecule kills the cell. Okay, so we are exploring the mechanism all the way we can. So here this is another, does the CBIQ binding exerts the conformational modulation in the tubulin? Means once any molecule binds with something, it does some conformational modulation in that particular molecule. So in my cases, if it does, how much it is? So we put at another molecule. This is like a, I will show you in the next graph probably. This is like a somewhere, here we use BCNS fluorescence to monitor. You know what, this is like some insect is here, what I cannot see, but I can feel the insect is here. So my hand cannot go here. So if I do this, this insect will go off. Okay, same thing we did here. This is called distal perturbation. Okay, so the BCNS, it does bind with tubulin in some other places where my molecule or colchicine does not. But we put this molecule in a colchicine binding site, and we have seen this is changing the bis fluorescence emission. So that means, and it is decreasing. When it is by BCNS binds with tubulin, the emission increases. So that means the BCNS, this molecule is coming off the protein. So it's a distal perturbation. This is an example of distal perturbation. Here we have done with in vitro, we have done with molecular dynamic simulation also with that, as well as other things. So this is so this particular thing induces tells us that CBIQ binding tubulin may induces conformational changes in the tubulin leading to the reduction of BCNS binding. And then we went further. If it does bind with that, is there any modification of cysteine group? So this is a sulfohydride, means this is an SS bond. Okay, so this chemical modification, if you react with RSH kind of thing, so then this particular reagent gives you this and this. From simple absorption measurement, you can monitor this particular, you measure the monitor of any one of these, particularly absorbance of this. So or absorbance of this molecule, this will decrease, this will increase. Okay, once the reaction is going on. So same thing we do it with not instead of RSH, the tubulin and this and my molecule, and see. So this is called the modification of cysteine groups on the sulfhydryl specific reagent DTNB. This is the reagent DTNB we put in the tubulin, and then we see that how much this SS bond is means disturbed, and then with the red one, with my molecule, the black one is without the molecule, red one is with the molecule. So and then we saw that we quantified the 1.5, 1.4 cysteine residue is getting disturbed. Okay, so these are the mechanistic details actually. So then we went for these in silico studies, as I told you, the molecular docking, dynamic simulations with how many, what amino acids are responsible for these bindings and all. So even the molecular dynamic simulation also, how stable the molecule is. This is RMSF and RMSD study. And ultimately we went for the what is the my molecule is disrupting the microtubule. What is the mechanism? How does it do so? So first of all, we establish it is binding, it is changing the conformation slightly. So actually, you know what, this polymerization takes place. So in this, during this process, this polymerization process, they have to, this alpha and beta tubulin, they have to come straight. They have to come in a particular conformation. Then only they can form a tubulin aggregates, which we say microtubules. But this, once this molecule is attached, when this molecule is introduced, this molecule binds with the alpha and beta, both the tubulins. Okay, and it does not allow this alpha and beta tubulin coming to a straight conformation and form this particular aggregates. And even after the microtubule also, if it is formed, so if you introduce it, this just started interacting with that and depolymerize the P-form microtubules. So that's the way we propose. So it may works in this particular mechanism. So then we put this unveiling the potential of unfused bichromophoric naphthalimide, because there are lots of studies with the fused naphthalamides. So here is an unfused naphthalamides to induce the cytotoxicity binding to tubulins. This breaks the monotony of the what I am reading, why I am reading it. This breaks the monotony of the naphthalamides as a conventional intercalators. So naphthalimide means people thinks that it's a conventional intercalator, but we have shown this is a naphthalimide, another group we have attached. And believe me, we have done this with all GCDs, ATDs, DNA, but it does not work with DNA at all. Okay, so it breaks the monotony that naphthalimide means a classical intercalator. It is not the case. So then again we went further. This is one molecule, this is another case studies. We went for this another series of molecules. I'll tell you only one here for the breast cancer, and specifically TNBC means triple negative breast cancer. Okay, which is very, very dangerous. As you know that breast cancers it's a deadly disease now, and forget about the deadly disease. Lots of breast cancer patients are there in India as well as all over the world because of the heredity, lifestyle, age, means the obesity, diabetes, hormones. Okay, so this is the classification of the breast cancer on basis of the immunohistochemical profile. So it's ER positive, PR positive, HER negative, and then if it is then proliferation is low, prognosis is also better, and the treatment is such like that. So but believe me, these two are so dangerous. This triple negative breast cancer, this is Basel-like and Claudine law. So this is all negative, UR negative, PR negative, HR negative, and of course this is too, this is very high and worse. So we thought, so we started with this, and we put it some. Yeah, so this is the some drugs which is used for the triple negative breast cancer, but it has some its own disadvantages too. These are the used in the hospitals for the combination therapy or monotherapy, depending on the type of breast cancer it is. And then we went further. So we designed some small molecules which is taken. This is not the my molecules. This is the molecule which inspire us to go further. Is a podophylletoxins. Okay, so it went I think level 4 clinical trial, and then it fails because of it's a gastrointestinal problem of the patient. So podophylletoxins. So we thought, okay, if podophylletoxins can work, why not the azapodophylletoxins? So we put it the nitrogen analog of the podophylletoxins, which is actually this is the podophylletoxins, and this is the nitrogen analog. You see the structure is same, only this weight by this, and we have many, means 17, 18 compounds of this. That's the structural variant, and we have done this QSR properties studies. In some cases, one methoxy out is completely gone. And the IC50 value of this or LC50 value of this particular molecule is in nanomolar, 300 nanomolar, 400 nanomolar. Okay, so we have a series of molecules, and then we went for these are the IC50 and GI50 and LC50 value of the particular molecule what I have shown. One molecule I am showing it here, and all 30 cancer cell lines we have studied in NCI, National Cancer Institute in USA. So, and then we went for this theragonistic approach of this azobodophylotoxins. We put it in the in physiological environment. We saw this anti-cancer activity of this particular molecule. We went for the mechanism. What mechanism? This fellow is extremely working, believe me. This is some of the molecules of the series of molecules is already put for patent, and this is very effective, as well as the tinoposide, etoposides, and with that azobodophylotoxins also. So, and then we went for this, what is the mechanism of it, and then multi-targeted potential capacity of this particular molecule, we name it, it's an HTDQ, and then delivery of HTDQ also. These two parts I will not discuss because of the time, but certainly we go for this mechanism. So here again we studied all these spectroscopic studies of this particular molecule to see its emission, okay, or imaging capabilities by this particular molecule. And as not only this imaging capability, it helps us to find out the mechanism of action. So these are the so here these are the again quantum chemical calculations to support this in vitro observations of emission measurement specially. Then all this hydrogen bonding, this is the solvation and solvation dynamics. This is the role of hydrogen bondings, and then we went further for this MTT assay of the cytotoxicity studies of this particular thing. We have taken two triple negative breast cancer cell, MDA MB231, MDA MB468. IC50 value is, this one is 937 nanomolar. This is, I think if we repeat it, it will be lower than that also, okay. So, and then we went for this cell morphological analysis of those particular two triple negative breast cancer cells, and then we went for to take this means to understand the mechanism. We study all with the apoptotic marker study with this PARP1, procaspase3, BCL2, BAX and all. So, and then the increased expression of cleaved PARP1 and procaspase3 suggesting activation of the apoptotic process. And the unregulated pro-apoptotic BAX expression inhibiting, this is also, this whole thing tells us this is working as an apoptotic marker, okay. So it works in the, then this is a very interesting study, is a 3D tumor model. So nowadays it's a mimicking the tumor cell. Actually these are the human breast carcinoma cell. Triple negative human breast carcinoma cell that we form like a cube, a cuboid kind of thing. We form a ball with this human triple negative breast cancer cell, and then we put our compound into it. We put our compound into it, and after certain time, you see, we have seen this is with the 500 nanomolar compound, the percentage of the area of the spheroid, we say it's a tumor spheroid. Nowadays it's going on actually, the tumor spheroid. This is equally good like you are injecting this thing to a person who is having this tumor, okay. So that we cannot do it without the FDA approvals and all. So the thing is, so here we take this cell out, put our compound and see the spheroid growth is decreased or not, okay. So this is exactly what people are doing in hospitals. They are putting you this anti-cancer drug, and after certain time the anti-cancer, the chemotherapeutic drug is not only used to kill the cells but also used to reduce the size of the tumor. Suppose some tumors are so big, it's very difficult to operate. So you might have seen in the hospitals they tell some patient, you come after 3 cycles of chemotherapy, okay, and then we will operate it. It's not just the operation, chemotherapy and radiotherapy. It can go in any way depending on the stages of the cancer and depending on the size of the tumor, depending on the property, means all solid tumors are not same actually. Depending on the tumor, what do I say? Means the property or tumor type, I say rather than type. So here we did that. So human breast carcinoma triple negative cells, we put a spheroid and we did that. And not only this, we take another one. This is a 41 cell lines, okay. So that also we take, and here also spheroid is size is decreasing, but not like the other one. Here decrement is little bit less. So then we went further for the cytotoxicity study and all those mechanistic details. And then we, of course, we published it. So this is with these two cancer cells. Now I'll tell you something else. This is for the brain imaging. This is another molecular engineering what we did is for the brain imaging. Okay. So, so brain imaging, you know, the dopamine and specifically we work for this, for the Alzheimer disease. Okay. So amyloid beta is a protein which aggregates and forms the fibril. Okay. So that amyloid fibrils is a reason for Alzheimer. Once the Alzheimer disease is there, you cannot cure, because the fibril you cannot bring it back to amyloid, beta amyloid. So what you can do is, you can, giving the medicine, you can retard the formation of the amyloid fibrils. So we take this opportunity and we thought, okay, there is a molecule, this particular molecule which is used in the hospital is for clinoquinol. So clinoquinol is used for the amyloid detection, most the targeting the metals. You know that we need metals for our body for sure, for any metals, copper, irons, because metal enzymes are there in our body. But excessive metal deposition in brain cause the aggregate, means causes the accelerating the aggregation process of your amyloid beta protein. So clinoquinol is used, and another molecule is also used for the brain imaging. So clinoquinol is used for the therapeutic purpose, and THT means thioplavin T is used for the brain imaging in hospitals. So what it does actually, clinoquinol, as I told you, it has a nitrogen, so oxygen also, so it chelates the metal ions. And the thioplavin T, it went to the brain. It has a localization in the the region, we said amyloidogenic region, where this amyloid fibril takes place. So thioplavin T goes, if there is a normal monomer, amyloid beta monomer, this thioplavin T fluorescence is less, and if it is binds with the fibrils, thioplavin fluorescence is high. So detecting that, people are nowadays is using how much fibril formation is there. So we took the advantage of that. We fuse these two molecules, and we take this particular part from this thioplavin T, and with this particular part from clinoquinol, we put a molecule and we synthesize a molecule which is called CBMDP. We gave the name according to the IUPAC name of this particular molecule, and then we put it. Of course, we did all these things. It is a theragnostic molecules. Imaging characteristics also we have to consider. We did all the photophysical studies of this particular thing throughout the solvents, and with the quantum chemical calculations, of course, to explain that. And then we put, so I think I have, yeah. So this is the molecule, and then what we did is, do we have this? Yes. So we put the molecules means with the amyloid beta protein, amyloid beta 40, amyloid beta 42. That protein we take, and in vitro interaction we study. We allow, if you see this red one, this thioplavin T, A beta, and copper. We give with and without copper, means we allow this A beta 40 to form an aggregate. We monitor its aggregation pattern. We put copper into it, and see its aggregation is happening very fast here with the copper, and this is the blue one is my molecules with my. So we put amyloid beta, we put copper, we put our molecules. So we see this aggregation is decreased a lot. Means, so this is cannot disaggregate, as I told you, no molecule cannot disaggregate the fibril formed fibril, but it certainly retards the formation of the fibrils. So this means it has a huge potential for the amyloid disease or the Alzheimer disease. Okay, so then we went further for the molecular dynamic simulation. Look at this. So this is the 50 nanosecond studies. Here, this is the amyloid beta protein. We put, this is without molecule. You see the structural, if you put it in extracellular fluid, this amyloid protein, no, this protein, you see the structure of the protein is getting lost. So this is the molecular dynamic simulation of only amyloid beta protein, A beta 40, and this is the A beta 40 with my molecule. Look at here, the structural integrity retained in my molecule, but in other case the upper case structural integrity lost. So that means my molecule is not only stabilizing the monomer. This is a monomer study, okay, and then whatever you have seen here, this is an aggregation studies. Okay, not only stabilizing the monomer, but also helping by stabilizing the monomer, it is retarding this aggregation process. So this molecule may be used for the Alzheimer's disease also. So this is targeted to Alzheimer only. So that's why we went. Then another molecules, we did it for the anti-cancer activities and all. So, so the suggestion. So what we do actually, we practice science with purpose. It's not that one n number of molecule we synthesize. We don't do that actually. Neither we have time, nor we have that much of money, not mostly we do not have wish to do that. Rather, we find the target, so then we sit on it on 6 months or more, and then we finally start the synthesizing the molecule. So practice science with purpose, remembering these things, because little drops of water and little grain of sand makes the mighty ocean and the pleasant land. So we think slow. So I believe start something. If you want to start something with small. Okay, then only we will go by, because here you modify yourself, means your current state, you put some action, you will get some result, then you will result, you come back to another small action, you will get some result. So this result will achieve you to go here, somewhere here. Okay, so that's in summary. So for courageous people, door is open, and we certainly, if you do join with us, we certainly help you to fly. And these are the acknowledgement for these are the people who worked with me during whatever slides I have presented here. So they are now almost all are assistant professor, well established. So Ritika is there in assistant professor in ICT Mumbai, and Himang is there in Halifax. Manoj Kumar, he is also assistant professor in ICT Mumbai. Romesh is there, and now he was in Virginia Tech, now in MIT Boston. And then Soham is in Cornell University, Piyush is with me right now. And these are the people who helped me for many ways. And of course, the funding agency. And these are the groups, those are the people who worked in this particular things. Whatever I have showed, means all are established now. And these are my present group. So we are doing molecular, right now we are doing molecular engineering for two purposes. One is for the biophysical chemistry, whatever I have shown you here, and another is for the molecular engineering for the optoelectronics. These three, these are all PhD students. Okay, so yeah, so C is project student, he is also project student here present. So they are working in the molecular engineering, and this in biophysical chemistry, and this is the molecular engineering in optoelectronics. And thank you all. You can ask anything, whatever you want.
So now the session is open for discussions and questions.
Yeah.
Thank you very much for a very nice lecture and interesting topics. You mentioned that
yeah, 1 hour you told me, right?
That your shift bases are complexating kappa and so on. Did you measure directly the complexating properties also of this, or just the interaction with the other thing? And second question, when it's copper complexating, is it also with iron or other things? What is there?
We did it. Actually, that was an obvious, thank you for a very good question, because that was an obvious question for the reviewer as well. So we did this complexation studies as a copper as well as iron also. and we have seen this copper complex actually since because of the time he told me 1 hour, so I finished in exactly 1 hour, otherwise I could have put that slide itself here. So it is forming a complex with copper, and I cannot say it does not form with complex, but constant is very, means binding constant is very less as compared to copper one, the iron one. So one more thing I want to tell you in this regard is we were unable to actually to find out this means complex in vitro, just in the laboratory itself, copper and this molecule, that we could not, because the complex was probably unstable or something. But in spectroscopy, we definitely did this the formation of the complex, that the peak is decreasing, another peak is forming. So that way we did. Since we tried once or twice for this to measure to get the complex and study the properties of the complex, that was not done. But it does work, reacts with copper, and then only we went for that particular study, because this is obvious to see that one. Until and unless it binds with copper, you cannot see that where with the copper it is the time is is increasing actually. Yeah. Anything. No question is a stupid question. So anything means, maybe, you know, we learn every day from the students. We learn every day from the students. Means you are asking something which we never thought of.
Sir, I wanted to know about these theragnostics more. So regarding the molecules which you developed, so their primary purpose is to act as a therapeutic agent, and they will also be concentrating in those tumors so that we can see their location. Means, are they being targeted to the tumor? Is this the purpose?
Yes. The real-time monitoring of the suppose we are putting this normally what it does for any other purposes. So for diagnosis purpose you need co-stain. Okay, so once this is this, then another injection is there, so that is stain. That's not a medicine. And to see that how much this tumor is decreased or what happened. But if suppose we use a molecule which itself will be a therapeutic activity, and as well as it will give us the image of that particular environment, so that's a win-win situation. We don't need to add another staining things. So real-time monitoring is also, you can do it, as well as imaging thing is also you can taken care of.
So that means when such molecules are in the clinical practice, so doctors will be able to monitor the size of tumor.
Size of tumor, as well as how this is what is the actual picture, where it is localized and all. So now we are adding it to it, like I told, we are adding some cleavable bond with this particular molecules. We put this as a probes with some cleavable bond. Of course, I will not tell that bond what is that, and you will deliver there. So that delivering thing we are taking care now. So it will deliver to the particular cell, and overexpression of something, and as it will cut it, this molecule will stay, and this property also it will show.
So indeed a very good feature to be added in anti-cancer drugs.
Yes.
So nice.
Yes.
Thank you, sir.
Yes. This theragnostic small molecule actually. Yeah.
Yeah.
And particularly for this particular molecule, no, CBMDP, we use all these Lipinski parameter, even blood-brain barrier, and everything it is satisfied. Everything it is satisfied.
Hello, good afternoon, sir. Thank you. Discuss good topic for. I would like to ask, what are the key clinical trials currently evaluating cancer theranostic agents?
I'm not getting. Could you please once again?
What are the key clinical trials currently evaluating cancer theranostic agents?
I told no in the second slide. So nowadays they are using this gold nanoparticles and some other things. Okay, dendriomas. So that we are using. That's for this as a therapeutic and as diagnostic purpose. So that is going on, not only clinical trials, this is they are practicing. People are practicing in hospitals also. So this is little bit different. It has not gone to that level so far, but we wish it will go.
Thank you, sir. Thank you, sir. One more question.
Yeah. Anything you ask.
Can we use nanotechnology for cancer treatment? It is possible. Then how it detect cancer cell?
Okay, so that you can Google it also, but I am telling you. So nanotechnology means it's a which way you are two ways. Okay, so it's a nanomedicines, or are you using for a therapeutic purpose or diagnostic purpose? So sometimes it is used as a to deliver the things. So it will carry this and to that cell localize it. Then it went off because its ADME properties means specifically nano. They are saying nano carriers. Even dendriomas also nano carriers. Okay, so they are that way. This is using nanomedicine is also used, which is like means take the advantage of its blinking behaviors. Okay, so it blinks, so it gives emissions. So that way also it is getting used. So nanomedicine, nanotechnology in medicines, there are many ways. So there's another different area. This is there. It's already there.
Any other questions from the audience?
Diagnostic are mostly connected actually with Protex. Do you know Protex?
Sorry?
Protex, these are proteolysis chimeric compounds where you add some binding structures, had a linker, and then you add some lysome inhibitor or lysome binder, so also a triplet of different structures.
Correct.
And then your target is destroyed by the proteolysis in this way. So
correct.
that could also be very helpful approach in this thing, and there are numerous things described already, and when most things are actually published in diagnostics, then most of them are really Protex, or these Protex approaches.
Yeah, that is used. Yeah. That is used actually. Yeah. Any other questions, please? Anything?
Any more questions?
Anybody?
Sir, one question on.
Yeah.
Sir, how?
How?
Sir, how to AI, artificial and intelligence being integrated cancer theranostic?
That I think this particular session was there. YouTube, you see this YouTube link. So he is a space, but I have a wish to do that actually. I have a wish to do that.
Thank you, sir. I will
because
try.
of the time, so we cannot do it. So I have a wish to do that.
So if there is no more question, please join me in thanking Professor Ghosh for his excellent and informative presentations. And I believe you have learned so many things on this theranostic approach which was missing in our module. So that will be fulfilling the requirement, to get it very much precise. So with that, I'll close this session for now, and then, but don't leave, we'll be having the feedback form things on now, and then we'll go for the lunch. Okay, so please be here, and we'll be closing the sessions. Okay.